Okay, in this video, we're going to see another example of induction, but this time we're going to use induction to prove an inequality. So we're going to prove, and this comes from one of the exercises in the book, we're going to prove that n squared is strictly less than 3 to the n for all n. Now we're going to say in the natural numbers, but because our natural numbers, the way we define it, does not start at 0, and we want 0, we're going to add it in. Okay, so this is what we want to prove. It's an inequality that's true apparently for all natural numbers 0, 1, 2, 3, 4, so on and so forth. And so let's again just kind of play around first to see if we buy this. So let's plug in n equals 0, which is going to be the base case in this example. So then we say 0 squared is less than 3 to the 0. Well, of course, 0 squared is 0, 3 to the 0 is 1. So yeah, that's true. Okay, what about n equals 1? So now we're talking about 1 squared, which is 1, of course, less than 3 to the 1. Well, yeah, that's true, right? So, okay, let's see a slightly more interesting case here. So n equals 2. Now we get 2 squared is supposed to be less than 3 squared. Well, that also makes sense because they're both squared and one has a larger base here, so that makes sense. Okay, so again, that doesn't prove anything, but it gets us some familiarity with what we're doing here. The point is that we expect an exponent like 3 to the n to grow faster than something quadratic like n squared. Now we want to prove this, and so we get to assume, let's just play a little bit here before we prove this, we get to assume that n squared is less than 3 to the n, and we want to show that m plus 1 squared is less than 3 to the n plus 1. Now, because we have an inequality, students often are not used to working with inequalities very much. You're used to working with equalities. And when you're doing equalities, you have to just use algebra. You have to be a little bit clever, maybe how you group terms and things like that. But you need things to be exactly the same. But when you're doing inequalities, you're allowed to kind of grossly estimate things sometimes. So what do I mean by that? Let's start with the left-hand side. So first of all, let's just factor this out. So we get n squared plus 2m plus 1. Again, we want to try to use the inductive hypothesis. When I squared it out, I see an n squared, which lets me use the inductive hypothesis. So that means this n squared is less than 3 to the n, and I can't do anything with these other terms, right? All right. So what else can we do here, right? So, well, one thing that we can do here is I could try to replace 2n and 1 with n squared, and then use the inductive hypothesis again. Now, the problem with that, possibly, is 2n isn't always less than n squared. So, for instance, when is 2n less than n squared, and when is 1 less than n squared? Question mark. Well, okay, for 1, if we want it to be strictly less than, then well, maybe we don't care about strictly less than. Sorry, let's do less than or equal to, because we already have a strict less than in our inequality. We don't need the rest to be strict anymore. So for the second one, as soon as n is equal to 1 or bigger, right? So as long as n is bigger and equal to 1, this will be true. And for the first one, we notice as long as n is bigger and equal to 2, this will be true. Okay, so these are also things you could prove by induction. I'm going to let us take these facts as true for simple sort of quadratic and linear growth here. So that means if I want to, I could say that this is less than or equal to 3 to the n plus n squared plus n squared for n bigger than or equal to 2. Now that we have to be careful about because we're supposed to prove this for all n bigger than or equal to 0. So this inductive case will only work for n bigger than or equal to 2, but that's fine. We can just check the other cases one by one if we like. But now I get to use the inductive hypothesis again. So this is strictly less than 3 to the n plus 3 to the n plus 3 to the n. There are 3 of them, so I get that's equal to 3 times 3 to the n, and that's the same thing as 3 to the n plus 1. Okay, great. So that's going to work. This is like a sketch that we can use in the actual proof, but now that we've sketched it out in this particular way, we just have to be careful to do the induction so that this works, right? So we do have to be a little bit careful here. So let's go into the proof now, and we'll just take note of what we need to be careful of to carry out this plan. So in the proof, we proceed by induction. Now in the base case, though, we're just going to, we'll do a few cases, okay? So it's not strictly necessary to do induction this way, but because we have a goal in mind, we're going to check a few cases, not strictly because of induction requires us to, but because our method requires us to. So here we get 1, which is equal to 1 squared, which is less than 3 to the 1, which is equal to 3. We just want to write it out in a way that it's easy to follow, even if we're writing down things that are quite clear. Okay, so now that we've checked those 3 cases, the 3 bottom rungs are valid. We have 3 bottom rungs to our ladder. Now we can build up from there. So assume for n a natural number, but now specifically n bigger than or equal to 2, that n squared is less than 3 to the n. And we will show that n plus 1 squared is less than 3 to the m plus 1, which means we can walk up the ladder, right? Okay, so let's start off. So starting with the left hand side, we find, okay, unlike the proof sketch, we're going to be a little bit more careful about the details here. So we first are going to factor out here, sorry, expand, and then we're going to apply the inductive hypothesis. This is exactly what we did in the sketch. So now by applying the inductive hypothesis to the right hand side, we find n plus 1 squared is strictly less than 3 to the n plus 2 to the n plus 1. 2 times n, sorry. Okay, let's label that star because we're going to need to use this. So now notice that if n is bigger than or equal to 2, then 2 times m is less than. So we're going to give a proof. We don't need induction actually, because if n is bigger than or equal to 2, then 2 is less than n times n, but that's just equal to n squared. And if we start with 1, well, 1 is less than n, because n is bigger than or equal to 2. And so it's also less than if you multiply it twice. So that's good to go. Okay, so we actually do give a proof of this. We don't need induction for that because there's a way of proving the inequality without induction. So I give myself a little bit more room. So by applying both observations to star, we find, or let's just remind the reader again that we're in the case that n is equal to 2, that so again we get we get 1 plus 1 squared is strictly less. This is what we already had, but then we see that that's less than or equal to 3 to the n plus n squared plus n squared. Now that's less than 3 to the n plus 3 to the n plus 3 to the n, which is equal to 3 times. We're just showing the reader everything that's going on here, which is like 3 times 3 to the n, which is 3 to the power n plus 1. Perfect. So now, by induction, this must be true for all n in the natural numbers union 0. Okay, so here we see that if we like, we can choose to check several base cases to kind of start the base of our ladder off. And in this case, we are going to do the inductive case for n equals bigger than 2. And then we can we have the first 3 rungs of our ladder already taken care of, and then we can step every other rung from there on. And so that proves by induction, right? So perfect.